Good evening, ladies and gentlemen. It's a pleasure to welcome you every time to that we can bring a lecture, special lecture for you in the IUCAA series of public lectures on astronomy and astrophysics. Some of you have braved the rains and adverse conditions to come here, so we thank you right in the beginning for being here so regularly. And we have this week a special conference going on in IUCAA, the International Conference on Infrared Astronomy and Astrophysical Dust. Of course, to the astronomers, it's clear what it's all about, but to the visitors here from outside, you're curious about that. So for that, I will actually welcome on stage Professor Shantanu Rastogi, who's an associate of IUCAA, and he will introduce the event to you and also introduce today's speaker. Later, Professor Somakraj Chaudhary, who's our director, will present him a gift on behalf of the organizers of the conference for giving us this talk here. So,
thank you, Samir, for organizing this special lecture. So on behalf of the LOC and SOC of Infrared Astronomy and Astrophysical Dust Conference, which is going on today, was the first day. So you can see the title of the talk is on water, and it's very appropriate that it's raining. So that's what Professor Melnick said, so I am just repeating him. So I welcome Professor Melnick, and I wish to thank him to accept our invitation to give this talk. He is at the Center for Astrophysics in Harvard University. It is Harvard Smithsonian Center for Astrophysics, and he is working in the area of infrared astronomy and submillimeter astronomy for almost 50 years. So he has a lot of experience in this field, and you can see there are, on the first slide itself, there are a lot of telescopes and space satellites. So he has been involved in almost all of them in one way or the other, and he did his PhD from Cornell University, and since then he is at the Center for Astrophysics. So his interest is now in future projects for space. He has there is a project on a spectrophotometer for the history of the universe and exploring ices. So that is the SphereX project, in which he is the lead in the ices team, and he has many other space programs in which he has been advisor or he is directly involved. What he told me is that he has been to India earlier, and that too was the astrochemistry conference, IAU astrochemistry conference, and in fact that was the first IAU astrochemistry conference which was held in Goa, and the first one was held in India. So we have a good interest in astrochemistry, and now it's growing faster. So I would like to ask the director, Professor Somakraj Chaudhary, to, and then we'll start the lecture.
Are you sure you don't want to wait until after my talk?
Okay, I don't know what this is, but then you ask somebody to talk something.
Okay.
I give it to you with the
See, it's a token of appreciation for.
And thank you guys for
Thank you. Oh, sure. So it's a pleasure to be back in India after 30. Is this better? Yeah, it's a lot better. There aren't many interstellar species that we can hold in a bottle. There are some, but not many that we drink as avidly as water. And so it does hold a special place in our hearts. And as I hope I can convince you over the next hour, there are an abundance of reasons why astrophysically water is of great interest. And what I intend to do this evening is walk through a sort of timeline of our interest in and progress toward understanding water in the interstellar medium. And I'll close with a discussion of the future, which is by all accounts quite bright. So the motivation for this talk stems from a couple different areas of interest to astronomers. For the past 50 years, astronomers, starting with radio astronomers and then moving into the infrared, the submillimeter, the optical, have worked to understand how and where molecules form in the interstellar medium. At the same time, somewhat more recently, our colleagues in the exoplanet world have been amassing a growing list of exoplanets and exosolar systems, both of which have been fascinating endeavors, but they've been largely separate up until the time that protoplanetary disks, or so-called planet-forming disks, were discovered, and it was quickly realized that in order to make progress in understanding these creatures, we required inputs from both the astrochemistry world of the interstellar medium and, of course, the information that was now flowing in regarding not just planets around other stars, but their locations relative to the central star. Finally, what motivates us today and into the future are the really big questions. These were questions we couldn't imagine ourselves asking a couple decades ago, but given the progress I hope to summarize for you this evening, we're now audacious enough to be asking the question of how do these newly forming planets get the ingredients for life, and in particular, the one key ingredient that seems to be involved, namely water. So what I'll do is I'll start by discussing, reminiscing about the early years. That's what I define as 1969 to 1983. These encompass the first observations of water, plus very important insights into how water forms in the interstellar medium. I'll next move to the middle years, which I define as 1983 to 1995, in which a number of very important modeling papers came out with actual predictions for what we would observe. But I'll also discuss our bold observational attempts to observe the water, which tragically failed in most cases. The later years, 1995 to 2013, saw the dawn of the space age when it comes to water observations, and we'll see that water really then begins to yield its secrets. And I'll close with the future, 2019 and beyond. I'll briefly review some new space telescopes, some that are approved, some that are in the planning stages, that represent the convergence of astrochemistry, exoplanets, and the emerging field of exobiology. And basically, we want to get the answer to the question of how planets get their water and ultimately how life starts. Before I get into the details, a few disclaimers. There are many areas that have contributed to our understanding of water in the interstellar medium. Most notably, the understanding we've come to regarding the structure and dynamics of star-forming regions, which has seen inputs from observers of a number of different molecules. There are a lot of contributors to this story who work in labs and on computers to determine collisional rate coefficients that allow us to translate the line fluxes we observe into abundances. there are many technologists who have greatly advanced the sensitivity of our detectors, our heterodyne detectors, our incoherent detectors, and this has made an immeasurable contribution to the story I'll tell. And finally, I'm absolutely certain that I will fail to mention some important contributions, and for that I apologize up front. So let's start with the early years, the first observations. Of course, when the first molecules were detected in the interstellar medium, there were many people that wondered just how many molecules were there, and a lot of people wondered, might water be one of them? And that question was answered in 1969. Actually, the observations occurred in late 68. The paper came out in 1969, and it was led by Charlie Towns, who most of you may remember as being the Nobel Prize winner for the development of the laser. And he and his group were the first to measure the now routinely observed 22 gigahertz line of mazing water towards SAGB 2 and Orion. But it was something of a seminal discovery because it finally moved water from the realm of the imagination into reality. We knew that water was in the interstellar medium. Now, it turned out that this was made possible in part by the technological revolution in the radio wavelength range that saw water being detected toward the end of the 1960s. It was the sixth molecule detected, but because of the technological revolution, you could see that the dams broke, and in each decade since, we've seen a veritable explosion in the number of new and different molecules that have been detected. But the question quickly arose, how does water form? It's there, it's obviously there by virtue of the 22 gigahertz maser line, but nobody really had a good idea of how water forms. The notion that you have neutral molecules just sort of floating around in space, and you would have a hydrogen collide and stick, chemically react with an oxygen and then another hydrogen, you could quickly determine that that was not the likely process in the cold interstellar medium. But to the rescue came what I regard as one of the foundational papers by Eric Herbst, who's in the audience and attending the conference we're all at, and William Klemperer, also at Harvard. And what they found and published in this paper was a path to making water through a series of reactions involving neutral atoms and ions. And I won't get into the details, but this is sort of a cartoon version of it. It starts with a cosmic ray that ionizes H2, which then reacts with a neutral H2 and oxygen, and so on and so forth, until you get to H3O+, which dissociatively recombines and, among other things, forms water. And this was a path that seemed to work well in the cold interstellar medium. And the reason it works, I should say, is that because one of the atoms is charged, you have an attractive force now between it and the neutral atom that you didn't have with two neutral atoms. It's strong and it acts over a relatively long range compared certainly with two neutral atoms, and most importantly, it works at low temperatures. Here I show a plot. This isn't from Eric's paper, but it's been reproduced a number of times based on their scheme. And this is the log time in years to build up an abundance of water. And the process is modest, let's say. It's not a fast process. It's not an incredibly slow process, but it takes between something like 3,000 and 10,000 years to exceed a water abundance of about 10 to the minus 7 relative to H2. So that was in 72, I think it was. by 1976, 22 gigahertz observations of the water maser had become quite common. And in 1976, there was a new transition of water that was detected at 183 gigahertz. This was done on the Kuiper Airborne Observatory by Tom Kuiper and his group, no relation to Gerard Kuiper, after whom the aircraft was named. And unfortunately, this discovery appeared only in the bulletin of the American Astronomical Society without any interpretation offered. So it was interesting, but not illuminating. It gave us a hint that this was a multispectral discipline that we were entering, but there were still many, many things we did not know. In 1978, there was another seminal paper, in my opinion, by Bill Langer and Paul Goldsmith, who built upon the chemical scheme that Eric and Bill Klemper laid out and that I showed in that cartoon. And they analyzed the cooling power due to a number of different molecules, including water, for a range of molecular clouds with densities between about 100 and 1 million. And what they found was this. This is at 20 Kelvin and at 40 Kelvin. This is the total cooling. And I've tried to highlight the cooling in water and the cooling in O2, which we now know is not the case. But certainly between 20 Kelvin and 40 Kelvin, water ascends to be, in some cases, the dominant coolant, according to their paper. So this fueled an even greater interest in water. It was no longer just about discovering this, but also this important astrophysical component that it may be the single most important coolant of gas as it collapses to form stars, for example. Unfortunately, water at 20 to 40 K doesn't excite a lot of transitions. You know, this could be calculated even in the mid-70s. And in fact, here I show in this dashed line an excitation temperature, an energy above the ground state of 100 Kelvin. And you can see there's basically 4 transitions that lie below this threshold. Now, here I show this could also apply to the Kuiper Airborne Observatory as well as Sophia. They fly at comparable altitudes. But what I did is calculate the atmospheric transmission. This is 0 transmission. This is 100% transmission for the ground state line of ortho water for a relatively low amount of overhead zenith water vapor and a 45-degree telescope angle. And this is the rest frequency of water. What I show here is plus minus 400 kilometers per second, which would encompass pretty much every region in our galaxy. And you can see that even at 43,000 feet, it's impossible to observe this lowest lying water transition. And if you look at all the other transitions I highlighted, these are all plus minus 400 kilometers per second. You see that basically the atmosphere is totally opaque, and there's no hope of observing the water at the temperatures that Goldsmith and Langer investigated, at least from within the atmosphere. Then in 1978, Tom Phillips and his group observed an isotopic line of water. And this is important because we're battling the atmosphere, which is very rich in H2-16O. But their strategy is let's look at an isotopologue of water, H2-18O, for which the atmospheric lines can be, in some cases, as much as 500 times weaker because the abundance of H2-18O is 500 times less. And so they achieved a detection at 203 gigahertz. And under the assumption that this isotopic ratio of 16O to 18O is about 500, they derived an abundance, and this is the first time water abundance was actually derived from observations, of 10 to the minus 5. Remember that the scheme the ion neutral scheme yielded abundances of 10 to the minus 7, a few by 10 to the minus 7. And they note, and this is from their paper, that this is much larger, unfortunately it got cut off here, than the 10 to the minus 7 abundance ratio predicted by Herbst and Klemperer. And the last sentence of their paper is sort of prescient, and it says it's possible that H2O is formed outside of the scheme, meaning there's another way to form water. And in fact, in that year, 1978, Litzer and de Jong did lay out a second path to forming water. Their intention was to divine a way to form water in great abundance that might explain the maser emission. So they came up with a set of neutral-neutral reactions that work only at high temperatures for the reasons I mentioned earlier. So in this scheme now, you have at high temperatures oxygen combining with H2, forming OH, with another H2 to form water. This turns out to be very efficient and very fast, as I'll explain in a minute, but under very restrictive conditions. And that's because the activation energy for these reactions are quite high, much higher than you would get in a cold, quiescent molecular cloud. So this is from their paper. They showed the buildup of water abundance, and basically they note that this mechanism is so efficient that all of the gas phase oxygen that's not already tied up in CO, because the CO oxygen bond is strong and would not be broken, but all of the other oxygen and other molecules, and of course the atomic oxygen, would be available to be converted at high temperature into H2O. And rather than taking 3,000 or 10,000 years, this conversion is well on its way in as little as 10 years, according to this paper. In 1980, so we now had two mechanisms for forming water, but the observations were very scant at this point. In 1980, there was a third transition of H216O, in addition to the 22 gigahertz and 183 gigahertz transition. And this was obtained with a heterodyne receiver with very high spectral resolving power, and so they could measure a line width. And it was wide, which is consistent with the shock. And the region observed in Orion is the same region toward which vibrationally excited and high rotational transitions of H2 had been detected, which indicated high temperatures. And so this lent support to this scheme given by Litzer and de Jong in terms of the shock chemistry based on these two facts. Still, there was the question of, well, what kind of shocks are these? What, can it be just any shock? Is it a special shock? And in 1980, there was another seminal paper, in my opinion, by Bruce Drain, in which he laid out the parameters for a different kind of shock than people had been considering up to this point. People have been considering very fast shocks, hard shocks that dissociate all the molecules that they impact. A C-type shock, the C stands for continuous variables, meaning that there isn't a jump in temperature or a sudden jump in temperature or density. And so you can think of this as sort of a gentler shock. So it's non-dissociative over a large range of velocities, which means that the pre-shock molecules can survive and are just warm but not destroyed, and this has a profound effect. And the effect it has is to now provide an explanation for the highly excited H2, the highly excited CO that was beginning to be observed routinely, particularly toward a source like Orion in the late 70s and early 80s. And what was interesting is Bruce Drain and Roberge and independently Chernoff, Hollenbach, and McKee undertook to model the emission from Orion, and independently they came up with parameters that were remarkably similar, I think, using this sea-shock approach. And what was particularly interesting is, at least for Orion, it implied that the unobserved water, largely unobserved, except maybe for that previous transition, should be very highly abundant. All of the O being converted into water that's not in CO. A year later, Drain, Roberge, and Delgarno came out with a paper that generalized the shock model. It wasn't targeted toward Orion. These were models that could be applied to any region for which you knew the shock velocity and the density. But the key takeaways is that in all of these cases, and these are 10 to the 6th, 10 to the 4th, and 100 per cubic centimeter for the hydrogen, water is a major gas coolant, which is a broad range of parameter space. And at the higher densities, as pertains in Orion and other places, water is, according to these models, the dominant cooler of the gas. So by 1983, as we closed this early chapter, we knew there was water in the interstellar medium. We had two viable chemical models for how water forms in the interstellar medium. The models suggested that water would be a major gas coolant in both the cold gas from Goldsmith and Langer and the warm gas from these shock models. And as I noted, the shock models predicted very high water abundances. So we had a sense that pursuing our understanding of water was not just pursuing our interest in this, but something very important in terms of understanding astrophysics. So it's not only familiar to us, but it plays this important role. The problem is we didn't have a clear idea of which non-maser water lines to target, and we had even less of an idea how to go about observing them. So now we move to the middle years, 83 to 95. In 1985, there was this very interesting paper by Takahashi, Hollenbach, and Silk that filled this gap for the first time toward a cold quiescent gas that was contracting to form a star. And as you can see, this is wavelength, and this is a flux. The integrated intensities of a whole bunch of ortho water lines against a continuum. But when you looked at these specific transitions and their strengths, you quickly notice that the atmosphere blocks most of these lines. So it was great to have target lines to look for, but sadly none of them could be observed, at least within the atmosphere. So we needed to try harder. We needed to get above most of the atmosphere. So in 1985, I was part of a small group that built an infrared telescope that flew aboard the space shuttle. It did photometry from 2 to 120 microns, sort of a follow-up to IRAS. And it was also intended to assess the shuttle environment for what was called then the Shuttle Infrared Telescope, but later named the Spitzer Infrared Telescope. So Spitzer was originally envisioned to fly every few weeks, as it was then believed the shuttle would fly every few weeks in the cargo bay of the shuttle. And this telescope, as the shuttle went around the Earth, would scan back and forth and paint the sky and make these measurements. We launched on July 29th of 1985, and here's a picture of the telescope as it was about to scan. For people who know infrared Illuminati, this is Frank Lowe, this is Giovanni Fazio. Believe it or not, this is me here, and proof that not only stars age, but people age, sadly. And what we found, much to my chagrin, who envisioned a reflight of this telescope with a spectrometer on board to look for water, was that the background from the shuttle was very high, and in particular the water column density was 100 to 1,000 times larger than we had hoped for, and this was largely due to outgassing from the cargo bay, and believe it or not, urine dumps from the crew. So in any case, the shuttle was not the place to go after water, it turned out, and the Space Lab program on which this telescope flew ended in 1986 following the Challenger disaster. So a second thought I had was, let's go after high-lying lines, very highly excited lines, which are very weak in our atmosphere. Lines that are excited at temperatures of a few hundred degrees are very strong in our atmosphere, but lines that are excited at over 1,000 degrees tend to be weaker. So along with then graduate student David Neufeld, we calculated the line emission from a shock gas region based on the model of Drain and Roberge, and we considered all levels up to 7,700 degrees above the ground state. As an adjunct to this, we found that just the far IR lines alone of ortho water could account for 40% of the power input by the shock, the mechanical power input by the shock, which was quite impressive. And as I say, we had hoped to find water lines that were weak in the atmosphere. So in 1986, I proposed to use the 90-centimeter telescope aboard the Kuiper Airborne Observatory to observe some very high levels. These lines are weak in the atmosphere, but unfortunately for this attempt, they're also weak in Orion. The strategy here was, this is the atmospheric transmission, this being 0, this is 100% transmissive for these two transitions, one at about 400 Kelvin, the other at almost 4,000 Kelvin. And if you observe them at the right Doppler shift of Orion relative to the Earth, you can even move these lines totally out of their atmospheric counterpart because these lines are so narrow. But as I say, this ended with no detections. So the conclusion was we need to look at lower lying transitions, which meant we needed to go even higher. So what we did was we made some calls. We had at the CFA a 1 meter diameter telescope that Giovanni Fazio had flown 23 times. It worked like a charm, but I wanted to find a spectrometer we could use that we could just bolt on and go and do this quickly. So we teamed up with a group from University College London who had built a Fabry-Perot spectrometer, and we then went after some lower transitions than we attempted on the KO, but still modestly high. This shows the favored transition we were after at 81 microns, and at the proper Doppler shift, it was almost entirely out of its atmospheric counterpart. So we had a window to observe Orion between December 1st and April 4th, but because of bad weather, we only launched on April 2nd, with 2 days left in the window and not a lot of time in that window. We had a lot of time taken up getting to altitude with a number of usual problems. Ultimately, we did 10 scans on Orion during the very limited time we had left in this window. And the dotted lines are the Fabry-Perot in different orders, observation of the moon, and the scraggly line is what we got on these 10 scans only of Orion. The blue area is where we expected to see the water, and it is suggestive, but it was hardly something I felt comfortable publishing. And after spending 4 months in Fort Sumner, New Mexico, which is in the middle of nowhere, I basically said, enough. You gotta go to space. You just can't cheat Mother Nature within the atmosphere. So now we usher in the golden age, up until now, of the study of water from space. At the end of that balloon program, I proposed something called the sub-millimeter wave astronomy satellite, one of whose goals was to look at the ground state transition of water throughout the galaxy, but there were many other contributors at the same time, 6 in particular, and I show their launch dates here. There was the Infrared Space Observatory that was done by ESA, the mission I led, SWAS. There was a Swedish mission-led mission called Odin that was launched in 2001, of course Spitzer, and then Akari, and then Herschel. Now, these missions accumulated so much data and so much understanding of water that it is impossible to relate in even an hour, a full hour, let alone a fraction of an hour. And in fact, there have been entire conferences that have been filled with discussing the details of what these various missions have yielded. So what I will try to do is to summarize their collective results while standing on one leg, figuratively. Result number 1, outflow shocks do rapidly and very efficiently elevate the water abundance, though not quite as much as we expected initially. Here I show a plot of a shock velocity, and for a C-type shock, the peak post-shock temperature. So the faster the shock, the higher the peak post-shock temperature, and above about 40 kilometers per second, the post-shock temperature gets sufficiently high that you then begin to break down molecules. So the C shocks work at about 40 kilometers per second and lower. As an example, a shock with a very modest velocity of 11 kilometers per second has a 500-degree post-shock temperature, and at 20 kilometers per second, it's about 1,100 degrees. Now, here I show the time adjusted, the time to form water, to convert all the oxygen not in CO into water as a function of peak post-shock temperature, and here is log time in years. And you can see that for this canonical 11 kilometer per second shock, it takes about 600 years to convert all the oxygen into water, which is relatively short. But when you go to 20 kilometers a second, which is quite commonly seen in line profiles, that time can reduce to 2 years to convert all the oxygen into water. So it is a very efficient process, but further observation showed that the derived post-shock water abundances were typically between a few by 10 to the minus 7 and a few by 10 to the minus 5, less than the 10 to the minus 4 and slightly above that had been predicted. Michael Kaufman and I wrote a paper in 2015 that tried to explain that, and the explanation now seems, I would say, believable, because these shocks occur in sources close to protostars, which have prodigious far ultraviolet radiation associated with them, and that radiation ionizes a lot of the gas in the shock, which changes the shock structure itself, and will photodissociate water in the post-shock gas. So G naught here is the factor times the average far UV field in the solar neighborhood. So a G naught of 0 would be, sorry, a G naught of 1 is what we experience in the solar neighborhood. This is 10 times the far UV field in the solar neighborhood. And common to these is the fact that downstream of the shock, the water abundance drops. So given the environment in which these shocks were and the water abundances were measured, we think that this is sort of a believable addendum to what is otherwise a very clean and elegant model for water formation. And just to illustrate the point, I always thought that this was exceptionally beautiful. This is the star-forming region L1157. This is the near-infrared Spitzer IRAC image. And this is an image taken in a low-lying water transition, and just one of the spectra that go into this. The other two things we learned I'm presenting together because they're really tied, and that is we've learned that within quiescent molecular clouds, now no shocks, the gas phase of water is mostly a surface phenomenon. And the deeper into the clouds, you get large amounts of water, but it's in the form of ice. And it evokes a third mechanism for forming water that was discussed by a number of people at our conference earlier today. And simply put, it involves both hydrogen and water striking grains. A hydrogen strikes the grain, and in a relatively short amount of time finds an O to form OH, and then another H comes along, forms water, and it sits on the grain until something may remove it. And so this is the picture that emerges from these several missions. Here I show the depth into a dense quiescent cloud, in this case in AV, and the gas phase water abundance, and this red line here is the profile of this water abundance. And within about 3 AV into the cloud, the abundance remains low because the far UV can just photodissociate any water that's either formed on grains and photodissolved or formed in the gas. At intermediate distances into the cloud, between about 3 and 8 AV into the cloud, you have this balance. The far UV field is now attenuated, so you're no longer photo-destroying the water that is in the gas that rapidly, but you will photo-desorb water that's formed on the grains. And once that water is photo-desorbed, it can be photo-destroyed. And these processes each have their rates, and when you look at it in detail, they balance out to a peak water abundance of a few by 10 to the minus 7. And then, of course, deep into the cloud, the dust grains have basically totally attenuated the far UV radiation, so you no longer have a mechanism to get the water off the grains, and it just freezes out, and the gas phase water abundance plummets. We did some calculations in 2009 of this process. The solid lines are the gas phase water, the dashed lines are water ice, and basically what we're showing is the abundance here versus depth into the cloud. In this case, for 3 different values of this G0 parameter that parameterizes the far UV field, and in this case, for densities of 10 to the third, 10 to the fourth, and 10 to the fifth. But the result is that this balancing act moves the peak abundance deeper into the cloud as the G0 goes up or the density goes up. But the most important takeaway for this talk is that what we found is that the ice abundance was about 1,000 times higher than the peak gas abundance. So this is obviously a very important prediction, and it needs testing, and I'll describe a mission that will test that shortly. This is a map of quiescent water. This is the Orion Ridge, and in a paper that was recently submitted, we show that this water has to exist in a layer very near the surface of the clouds. The intensity of the water emission, there are about 1,000 spectra that go into this, does not correlate with the CO, which we know traces the volume of the gas, the whole depth of the gas. And they're somewhat anti-correlated, which, among other reasons, leads us to believe and confirm this notion that this water resides near the surface of the cloud. So, again, condensing these 6 missions into a few summary points, some combination of process 1, 2, and 3 can explain almost every source that's observed in water, from dense starless clouds to protoplanetary disks. So this is sort of the summary cartoon that encapsulates the 3 mechanisms the low temperature quiescent cloud way of getting to water, the post-shock way in high temperatures, and the water formation on grains. And they all lead to water. And this is the takeaway message for how water forms in the interstellar medium to the best of our knowledge. So now that we understand how water's formed, we want to understand how water gets to protoplanetary disks, and this is the next challenge, and it's a challenge for the future. And I'll describe 4 missions in closing that in some way or another will attempt to answer this question of the water content in planet-forming disks and hopefully a mechanism for how that water gets there. Well, we're all familiar with JWST, and JWST intersects with our interest in water in a couple ways, but it's useful to remind ourselves of JWST's power. It's about 10,000 times more sensitive than ISO, which provided our first measures of the water from space. It's 100 times more sensitive than the most sensitive instrument on Sophia, and 10 to 50 times more sensitive than Spitzer. JWST will have access to a number of H.2.16.0 ground rotational and vibrational transitions, but almost all of them in the JWST wavelength range probe warm to hot gas. JWST will also have access to almost all of the transitions, actually all of the transitions of rotational emission from molecular hydrogen, and can be used to better characterize the outflows from which we're now measuring and Herschel measured water. It can measure hot water in the inner regions of protoplanetary disks, and it can measure ice absorption, including the ice features at 3, 4.5, 6, and 13.3 microns. Sophia, the Stratospheric Observatory for Infrared Astronomy, is a joint project, for those who aren't familiar with it, between the US and Germany. It's a 2.5 meter telescope housed in a 747, flies between 41 and 45,000 feet, and carries one instrument now, and one we're building now and hope to install in a couple of years. The instrument that currently exists is EXES, this echelon cross-the-shell spectrograph, which has already been used to study vibrational water toward stars at around 6 microns. The second instrument is called Hermes, and will provide a range of spectral resolving powers from low for studying galaxies, namely around 600, to very high, about 100,000 or about 3 kilometers per second velocity resolution, over the spectral range of 25 to 122 microns. It basically combines a very large grating with Fabry-Perot etalons to do the very high resolution work, coupled with high efficiency transition edge sensor bolometers. The primary science goals, given this wavelength range, will be to look for gas phase transitions that we believe may be detectable from protoplanetary disks, and look at crystalline and amorphous water ice that actually emit at 43, 47, and 63 microns, depending on whether the ice is amorphous or crystalline. And this is a wavelength range that Herschel had no access to, Spitzer had no access to, and JWST has no access to. So this is somewhat unique to Hermes. In addition, we intend to go after the HD line as a tracer of the total gas column in protoplanetary disks, and I'll get into this in a moment with regard to another observatory, one of whose main focus is going after this line. The commissioning of Hermes is scheduled for the spring of 2021. Now, this third mission, with apologies to people who heard me give this talk earlier in the day, but for the benefit of people who weren't able to be there this morning, is SphereX. It's an all-sky spectral survey that will cover the wavelength range from 0.75 to 5 microns with a launch in 2023. It has three main science drivers. One is to probe the very earliest epochs in the universe's history, namely inflation through measures of non-Gaussianity, survey the Milky Way in biogenic ices, and measure the history of light production in constrained galaxy formation over cosmic time. And the leaders of these three different themes are listed here, and I'm leading this ice investigation. SphereX will fly in a sun-synchronous orbit, which means it flies at the terminator of day and night of the Earth every day through 365 days of the year, which means that every orbit takes it over the North Pole and the South Pole of the orbit, which means that these regions we cover hundreds of times in a 6-month interval, as opposed to a few times at the intermediate latitudes. So when we're at the pole, we'll do the extended background light measurements, which require very high sensitivity. When we're off the galactic plane, we'll do 3D galaxies, RA DEC and redshift for our inflation studies. And when we sweep across the galactic plane, we'll do our ice survey. So we'll build up spectra over several orbits. We will carry 6 2K by 2K infrared detectors of the sort being flown on JWST. The cooling system for this telescope is entirely passive, meaning no cryogens, no mechanical coolers, and at an expected temperature of the telescope of less than 80 Kelvin, we will be background limited to 5 microns. The detectors will be kept somewhat cooler through a special radiator. And the baseline mission is 2 years. We cover the entire sky every 6 months, so that means 4 independent all-sky surveys. Almost 14 billion positions will be sampled with our pixel size of 6.2 arc seconds. And there are no expendables, so this mission could go beyond the 2-year baseline. So as I hope I convinced you in the earlier slide, if you're interested in following the water, you really need to follow the ice, which is one of the things that SphereX is built to do. A summary of the instrument: it's a 20-centimeter telescope. It's small, but because we have a wide field of view and very sensitive detectors, it's extremely powerful. I covered these points and the 6.2 arc second pixels. As for sensitivity, for those familiar with the 2-mass survey, SphereX will go 4 magnitudes deeper than 2-mass, and we will obtain a solid detection, a high signal-to-noise detection of even the faintest Y sources. Of particular interest to us on SphereX is the 2.5 to 5 micron region. This is an ISO spectrum of W33A that shows why this region is so interesting. It's very dense in ice features, including water, methanol, CO2, 13 CO2. This is a CN stretch, CO, and a species called OCS. We will observe these in bands that have different spectral resolving powers, and the reason for that is we want to make sure that each one of these ice features is spectrally isolated and not blended in a way that will confuse us. So at a resolving power of 35, it's perfectly adequate to get the very broad water ice absorption feature and even the edge of the methanol. But the region in red, we bumped up the spectral resolving power so that we could get the methanol and we could clearly distinguish CO2 from 13 CO2. And the highest resolution, 130, is to separate the CO and the XCN features. And each of the underlying spectra here are actual spectra obtained at a resolving power of 700 using the short wavelength spectrometer on ISO. And you can see the overlay, which have been smoothed to these respective resolving powers because ice features are inherently broad compared to gas features. These resolving powers do a quite adequate job of reproducing the intrinsic ice spectra. So we expect that SphereX will increase the number of ice spectra currently available by a minimum of 100-fold, and as I'll show you in a second, maybe quite a bit more than 1,000-fold. Actually, I left those slides out for the sake of time, but it could be as much as 10,000-fold, but certainly anything between 100-fold and 10,000-fold is a huge improvement and a game changer. And how is it a game changer? This plot is from a very nice review by Adwin Bugart in Annual Reviews of Astronomy and Astrophysics. And here they plot different lines of sight toward 4 dark clouds and toward background stars that could be seen through these clouds at various depths through the clouds from the edge toward the center, and they measure the depth of the ice feature in water, CO, CO2, and methanol. And here you see the trend lines. As you go deeper into the cloud, the column density of water ice grows, and likewise with CO, CO2, and methanol. And what you can learn from this is where these best fit lines intersect this x-axis tells you where the onset of ice formation in these different species begins. And at any different vertical line here, you can just read off the y-axis and get the relative abundance of these different ices. So it's a very simple and straightforward experiment. And by sampling orders of magnitude more lines of sight than has ever been attempted before, we can improve the statistics in this plot significantly and get very accurate depths at which ices form, as well as their relative abundance as a function of depth into the cloud, which may change as you move into the cloud. And by sampling regions across the Milky Way, we sample different evolutionary stages from diffuse clouds to protoplanetary disks, so we can see how these ices and their composition evolve as they progress from these clouds to disks. Now, of course, I mentioned that JWST, and they will be operated at the same time, and JWST has the same wavelength coverage as the SphereX, but JWST is not a survey instrument. There is no hope that in a Hubble time, JWST could survey the Milky Way. It's excellent at doing very restricted regions, but far too time-consuming to do large area surveys. But because it is a big telescope and very sensitive, and it has higher spectral resolving power and greater wavelength coverage, we believe that SphereX and JWST can work hand in hand, wherein we provide very interesting targets for follow-up with JWST. So finally, I'd like to describe a project I've been involved in for the past 3 years, which is a study, which is one of 4 missions that NASA has funded in preparation for the 2020 Decadal Review. For those not familiar, in the US, we attempt to prioritize big ground-based and space-based projects in 10-year intervals on the decade, so 2010, 2020. And NASA has funded, over the past 3 years, the study of an infrared mission, an X-ray mission, a planet characterization mission, an exoplanet characterization mission, and a large UV optical infrared telescope, which is general purpose. I've been involved in origins, and sort of some of the key takeaways is that for reasons I'll explain in a moment, it's 1,000 times more sensitive than any infrared telescope previously flown. It carries a 5.9 meter diameter non-deployed, as opposed to what JWST has, cold aperture. And at 5.9 meters, it's the same collecting area as JWST. And it has 3 orders of magnitude of wavelength coverage, from 2.5 to almost 600 microns. The study wrapped up a couple months ago, and we submitted our report to NASA and the Decadal Committee on August 23rd of this year. This is a cutaway showing the 5.9 meter diameter mirror. To those familiar with Spitzer, this should look very recognizable. We intentionally tried to scale up the Spitzer design, which has worked exceptionally well. What is interesting here, though, for a sense of scale, is that the 1 meter secondary mirror is larger than the primary mirror on Spitzer. Here I show 3 instruments, a far infrared polarimeter with the characteristics shown here, the Origins survey spectrometer, which would cover a large wavelength range with variable selectable resolving powers, and an instrument that would be contributed by Japan, a mid-infrared spectrometer and camera and transit spectrometer. This is intended to study exoplanets between 2.8 and 20 microns with a modest spectral resolving power, but sufficient to do what we want. Now, what makes Origin so powerful? This is the natural background, which is set by zodiacal light. This is optics at 4.5 Kelvin. The background of the zodiacal light plus optics at 40 Kelvin, which would sort of, well, I'll say 40 Kelvin, 85, and 20. So it's the sum of the natural background and the telescope optics. And the choice of these temperatures was not accidental. They correspond to Origins, JWST, which actually cuts off about here. So this line is really fictitious, since JWST only goes to here. Herschel, which is also fictitious down here, it cut off at around 56 microns, and Sophia, which does have a broad wavelength coverage. But the important point is that about, for example, 70 microns, by cooling the telescope alone, the difference between the 3.5 meter Herschel and the 5.9 meter Origins does not explain this factor of 50,000. What explains it is the temperature change, the lower background. Even for medium resolution instruments, for which the background begins to become somewhat less important, we would be, if Origins is selected, 1,000 times more sensitive than the Herschel PAX instrument. So what can we do with this power when we want to study the water trail? And I created this plot because I think it says it all. If you just restrict your attention to H216O and H218O lines with an energy above the ground state of 1,000 Kelvin or less, you have one transition at 840 microns available to JWST, 3 transitions under exceptionally good weather conditions for ALMA, and you have, I forget it's 102 transitions of water. It's over 202. It's 102 and I think 101. So 203 transitions of H216O and H218O in the wavelength range that Origins would cover. So this would be extremely powerful for studying water in each of these domains. It would also have the wavelength coverage to study the ice emission features, as well as to ascertain, given the different predicted strengths of the 43 micron feature, the ice to rock ratio in debris disks. So Origins would be able to measure water in a number of very interesting domains in protoplanetary disks. We would be able to measure water on either side of the snow line, either in gas form or in ice form. And we would be able, it has the sensitivity to study 1,000 disks in 1,000 hours. And for reference, Spitzer and Herschel, over their lifetimes, only studied water in 5 disks. And the cold water detection with Herschel required 20 hours alone toward a very favorable source, TW Hydra. This shows in graphic form a comparison between the sensitivity in terms of the water content in Earth oceans of the various missions, JWST, Herschel, Spica, and Origins, for the different evolutionary stages of this so-called water trail. And you can see that Origins represents, in almost every case, a very significant advance. And I will close in a moment with what it can do with comets. But I mentioned HD earlier, and we now understand that there's a very tight connection between the material available in a protoplanetary disk and the planets that form in that disk. So it's critical for us to get a good measure of the gas mass of these disks, which is, of course, mostly in the form of molecular hydrogen. But there are problems. The first excited state of molecular hydrogen, rotational state of molecular hydrogen, is 510 K above the ground state. So you're not going to get any emission from molecular hydrogen in the disk midplane, which is at a temperature of 20 degrees and maybe sometimes a bit colder. In the interstellar medium, we use CO as a surrogate for H2 because we believe we know that the ratio of CO to H2 is about 10 to the minus 4, and that we apply it rightly or wrongly almost universally in our attempt to understand how much H2 is in a region in the interstellar medium. But in the midplane of protoplanetary disks, CO freezes out. And so whatever you measure in gas phase CO may not be reflective of the total gas content of the disk. And the dust to gas ratio doesn't work well because there's ample evidence that grains have already started to grow. And so the traditional methods that we apply in the interstellar medium, where the grains are relatively small, just cannot be transferred to studying planet-forming disks. And so that leaves HD as the best alternative. We believe that we have a pretty good handle within a factor of a few of the deuterium abundance relative to hydrogen, which is significantly less than the factors of maybe as much as 100 in the uncertainty in these approaches. They've both been applied to the same disks, and they've disagreed in the amount of gas that they predict by as much as a factor of 100. So we think HD is the best way to go after the gas mass in these disks. And the advantage that Origins brings over anything previously is that it's a combination, of course, of the sensitivity, but also the spectral resolving power. Spica will also be a cooled telescope, but it has much lower spectral resolving power, and the higher spectral resolving power is what amplifies the line to continuum ratio and makes the detections much clearer. And you can see that Origins will be able to measure the content of these disks, the mass of the gas in these disks, down to the level of Neptune mass. So we want to know how water gets to the planets that are forming in these disks. We think that comets may be a very good candidate for delivering that water, but there are questions. And the questions arise because here I'm showing the D to H ratio in ocean water. So here's the Earth, and the D to H ratio measured in these comets using HDO and water that have been measured toward these comets. And it's not clear that these really adhere to this line. You know, could this be a delivery mechanism, or maybe this just doesn't fit? So we know that water was formed at low temperatures given the D-H ratio that we measure. But is this diversity of comet populations real, or is it the statistics of small numbers? But with origins, we can measure very precisely the D-H ratio in 200 comets if they're available in 5 years, because we only need a few hundred hours to do it. So it's not a major project. So any comet that happens to come in, and many can be predicted, origins can get an accurate D-to-H ratio. And once we populate this graph with as many as 200 additional points, I think we'll be much further along the line of answering the question of is the water in comets consistent with the water in the Earth's ocean? So I'll close with a few points about measuring water in exoplanets. And one of the advantages I think that Origins presents over things like LUVOIR or HABEX is that we work farther into the infrared than those missions, which means that a 250K Earth-like planet relative to the flux of the star, and this is an M-dwarf star, is much less than the flux, if this plot continued, to a 5,000 degree star like the Earth. This would be about 10 orders of magnitude, and this is between 4 and 6 orders of magnitude. In addition, there are a number of strong biosignatures and bioindicators. Bioindicators, I would say, are molecular species that suggest that life is possible. Biosignatures are those species that we believe are only the result of life. And a lot of the strongest ones are in the region beyond about 2.5 microns. But of course, JWST has access to the same near-infrared region. But the difference is that the MIRI instrument and NIRSPEC were designed before it was envisioned that these sorts of measurements could be extremely valuable. So there was not a premium on making these instruments ultra stable. Well, why do you need ultra stable? Because you need ultra stable because you do not get a measure of this spectrum in a single transit. You have to co-average, in some cases, as many as 60 transits in order to build up the signal to noise through co-averaging that results in this sort of spectrum. And if your instrument is inherently not stable, then you can integrate over 10,000 transits and you'll just hit the noise floor of your instrument, which is what is shown for JWST here. But because we're going into origins with stability as a goal, we can do much better. And what that translates into is the following. Here I show what JWST can do for different molecules with its noise floor of 20 to 30 parts per million, and origins with a design goal of 5 parts per million noise floor. This is the signal detection, and you can see that we can do much more than JWST. So there is room for improvement on even JWST. Origins will be in pretty much the same orbit as JWST, namely the Lagrangian L2 position, and the launch, according to the study parameters we were asked to abide by, would be in 2035 or slightly beyond. So, in closing, we've come a long way in 50 years from this first detection of water through the maser transition to now detecting with very high signal to noise water produced in shock outflows and water on the surface of quiescent molecular gas. I think the future is looking very bright. The questions we're asking are some of the most fundamental that we pose to ourselves in astronomy, namely, How did we, the Earth, get here? How did the water get here? Might those same conditions prevail in other planets around other stars? And I think this next generation of telescopes will take us a long way toward answering that question. Thank you.
Thank you very much. So at the end of this talk, we have probably time for a question or two. Sure. The day has been long, and the conference has been going on since morning. So if there are any questions, please raise your hand. We'll come to you with a mic. We also have the lights in the auditorium. Thank you.
Hello. Thank you, Professor, for the nice talk. I have two questions which are simple in sense. Can you please explain in layman terms what do you mean by shock outflows, which you explained in the slides? And second question is like, can we differentiate amorphous ice and crystalline ice in terms of spectral parameters?
Okay, I'll take the first question first. We know that what we're seeing here is shock gas because at each position we get a spectrum and the lines are wide and not narrow. That's indicative of fast-moving gas. And what we think we're seeing here is when that fast-moving gas from the protostar, which is in the center, and is rocketing out in this direction and in this direction, and we can determine that these things are flowing in opposite directions from a whole host of similar outflow sources. We believe that where this very fast-moving outflow gas interacts with the quiescent gas, which is surrounding it, you set up a shock. So you have fast-moving gas slamming into basically slow or non-moving gas, relatively speaking, and that's where you get these C-type shocks. Now, with regard to the second question, we can determine the amount of crystalline versus amorphous ice because the amorphous ice has a very strong feature at 43 microns, and the crystalline ice has a strong feature at 47 microns. So they're spectrally separated, and it's that separation and their relative strengths that will give us, the answer to your question.
Which amorphous surrounds crystalline or crystalline surrounds amorphous?
I'm sorry, I didn't understand.
Which of the two surrounds which?
Well, it's really a question of the processing of the ice. It's not that one surrounds necessarily the other, but the difference may be, for example, in comets, how many times that comet has come close to the sun and been reheated, and then so they're really sort of two different flavors of ices rather than sort of a layer cake, as I understand it. There may be ice experts in the audience that will correct me, but I think I'm right about this.
Thanks.
Thank you. Any other questions for the professor? Well, I think the youngsters got a look at how astronomers, astrophysicists see their data and how ice looks in graphs as well and spectral lines. So that was a lovely talk. Thank you very much for honoring us with this talk. Thank you all for coming here. We'll end this session here, and please keep a lookout for other notices of other lovely talks which will come forth in the winters. Thank you very much.
Thank you.
Hello.